Hello everybody, welcome back to another abstract algebra video. Today we're going to be going over a problem from the August 2020 algebra preliminary exam at Virginia Tech. And the problem asks us to prove that any invertible matrix A with complex entries has a square root, meaning there exists a matrix B such that B squares to A. And the hint says use the Jordan canonical form. Before we do the proof of this, I want to show a quick example that demonstrates that this invertibility condition really is necessary. So here we have this 2 by 2 matrix. We can see it's not invertible just by taking the determinant, so we get 0. And to see that it doesn't have a square root, so let's suppose for contradiction that it did. So let's say A squares to 0, 1, 0, 0. Well, this means that the eigenvalues of A are 0. So what this means is that the characteristic polynomial of A is equal to x squared. Well, by Cayley-Hamilton, then A squared is equal to 0, and that's a contradiction. So we really do need this invertibility condition, and we should look out for it when we're doing the proof of this problem. So let's get started. Proof. So let's let A an invertible matrix. And the first thing I'm going to do is claim that it suffices to consider A in Jordan canonical form. So it suffices to consider A in Jordan canonical form. Reason for this being, well, suppose A is written as PJ P inverse, where J is the Jordan canonical form of A. Well, if J has a square root, so maybe instead of implication, oops, too much erasing. So I'll say, suppose we have PJP inverse, and let's say also that B squared is equal to J. Well, then A is equal to P, let's say B squared P inverse. But it's not too hard to see that this is the same thing as P inverse quantity squared. And well, this implies that A has a square root. All right, so let's assume that A is already in Jordan canonical form. And so maybe I'll write that first. So let A in Jordan canonical form. Since A is invertible, all its eigenvalues are non-zero. So in particular, let's write out what A looks like. It's going to look like some block diagonal matrix where I have, let's say, J1 through JL along the main diagonal, zeros everywhere else, and these JIs are the Jordan blocks of A. Great. We also know, so let's just select one of them. So I'll say consider, say Ji corresponding to the eigenvalue lambda not equal to 0 in C. Then we know that Ji is some m by m matrix, let's say, where it has lambdas along the main diagonal and ones on the super diagonal. So it looks something like this. And again, let's say this is m by m. Great. So because lambda is a non-zero value in C, I know it's going to have square roots. I can pick one of the square roots. It doesn't matter which one. So I'll say let mu a square root of lambda And what I'm going to claim next is that the following matrix is similar to Ji. So, or maybe let me write down a matrix first, and then I'll claim a related matrix is similar to Ji. So I'll say define, and let's call it Bi. So this is also going to be an m by m matrix. It's going to look exactly like J, except instead of lambdas, we're going to have mu's. So we're going to have mu, 0, then 1, mu, 0 going on, 0, 1, mu. Continue like this, and this will also be m by m. And my claim is that Bi squared is similar to Ji. So there's two pieces to proving this. The first is observing something about the eigenvalues of Bi squared. So before I write down what they are, let's notice, so Bi squared, this is going to look like mu squared, so that's lambda. We're going to have lambdas along the main diagonal. So lambda 0, On the super diagonal, we're going to have 2 times mu. And let's see, everywhere else, so above the super diagonal, it's going to be some other stuff. It's not really going to matter what it is, though, for us. So there's 2 mu. And let's see, like this. Maybe I'll put 2 mu here as well. And zeros. This is also m by m. So just looking at this, and it looks like the 0 here. Oops, sorry, this should be a lambda. So we can read off, well, Bi squared, the only eigenvalues are lambda. So Bi squared, lambda is its only eigenvalue. And I want to argue that it's similar to Ji. Well, Ji is already in Jordan canonical form. So I need to figure out, well, what's the Jordan canonical form of Bi squared? I know lambda is its only eigenvalue. If I can figure out the geometric multiplicity of lambda, then that tells me how many Jordan blocks are in the decomposition. And the claim is that, well, it's geometric multiplicity 1. So we'll see that lambda is of geometric multiplicity 1. Remember, this is the dimension of the eigenspace corresponding to lambda. So to see this, notice that Bi squared minus lambda I. All right, so this is going to be equal to zeros along the main diagonal. So 0, 0 going on. Let's see, 2 mu here, then 0, then something else here, and let's say we're going to have 2 mu 0, continuing like this, and again, m by m. So we can see here this first column is all zeros. So we're interested in saying, well, what are the number of linearly independent columns in this matrix? So 0 definitely doesn't contribute to it, but I'll leave this as an exercise. So exercise. Maybe I'll call these like the starred columns. So starred columns are linearly independent. Sorry everyone, editing me here. I can't believe I forgot to say this in the video, but part of the exercise in proving that these columns are linearly independent is using the fact that mu is not equal to 0, so that's where this invertibility really comes in. All right, I'll pass it back to past me. And that's enough to tell us that this lambda is of geometric multiplicity 1. So what that means is that the Jordan canonical form of Bi squared, it consists of a single Jordan block with lambdas along the main diagonal and ones on the super diagonal. So in particular, we know that Bi squared is similar to lambda 0, 1, lambda 0. And if we kind of compare this with where we were before, notice this is exactly Ji. So Bi squared is similar to Ji. All right, now we're almost there. So Remember, A is written in Jordan canonical form already. So let's kind of come down here. So we'll say A similar to, or it's actually equal to, we're assuming it's in Jordan canonical form. So J1 through JL, I think was what I was using. Well, I know each of these JI's is similar to a BI squared. This is going to be similar to, let's say, B1 squared through BL squared. And because this is a block diagonal matrix, this is the same as looking at B1 through BL squared, quantity squared or matrix squared. And this is enough to say, well, A is similar to the square of a matrix, and our argument to show that we can consider A in Jordan canonical form also shows that, this is enough to say that A has a square root. So, all right, thanks for watching, everybody. If you're a current student of mine studying for the algebra qual, please let me know if you have any questions about this. You can always leave questions in the comments as well. And I look forward to seeing you all in the next video.